Hey, Honors Calc, put this on double speed right now if you're listening. I want to do some more Trig review for everybody. So this is actually the Trig cheat sheet from Paul's online textbook, which you know I love. Ha ha! These cheat sheets are beautiful summaries. So I'm not sure what specifically with regard to trig needs to be reviewed, but this is a great resource. It even goes down to break down what we like to say SO, CA, TOA. Sine is opposite over hypotenuse, cosine adjacent over hypotenuse, and tangent opposite over adjacent. And for this definition, when we're talking about the triangular definition, we're assuming that this angle is between 0 and 90 degrees, because then you start getting with the obtuse triangle. We're basically assuming it's a right triangle, which is somewhat intuitive, I think. The unit circle, of course, is called the unit circle because the radius is 1, meaning the hypotenuse is 1. So what that ends up meaning is if we're, for instance, the sine is opposite over hypotenuse, well, in this case, it's then the opposite over 1. So that's what makes the unit circle so nice to work with, because the y value is quite simply sine, and the x value is just cos, and then tangent is that ratio y over x. And all the inverse trig functions are just those inverses. So this gets a little bit more specific into this idea of the domain. What are the possibilities for sine and cosine? It can be any angle. However, there's then limitations though for ones that are then reciprocals of those both, or tangent or cotangent. Basically, think about what's in the denominator. That can't be 0. That doesn't really been coming up, so maybe I should pick and choose. Here are some interesting formulas and identities. So I think this was the one I was sort of trying to reference today. I think I actually referenced it incorrectly in class. But the cosine of negative theta is the same as cosine of theta, which makes sense because if you think about my unit circle here, let's say I have the cos of 30 degrees, which we all know is the x value there. So the cos of 30 degrees would be root 3 over 2. Well, or I should say maybe pi over 6, right? Well, if we think about the negative pi over 6, that's just negative 30 degrees. But that x value is the same for both. So that's why some of these identities, I think it's hard to memorize them, but they all come from common sense in terms of if we were to go negatively, well, the sine of negative theta is going to be negative sine. So, right, this is 1/2 vertical displacement, whereas for the sine of negative pi over 6, it would be negative 1/2. So those are some of the identities that will allow you to simplify from time to time. We've got also these double angle formulas, the degrees to radian formula, and of course the unit circle. So this is really what I find to be most helpful to just have an idea. And really, there's only 3 ratios you need to know. That's 1/2, root 3 over 2, and then root 2 over 2. And all of these either multiples of 30 or 60 degrees or 45 degrees, they're going to just come, they're all going to be one of these. Just know that root 3 over 2 is longer than 1/2. So for instance, for this pi over 6 angle, you can see the x value, or the cosine, is root 3 over 2. The sine is 1/2. Those are flipped for 60 degrees. Whereas for a 45 degree angle or a pi over 4 radian angle, it's just root 2 over 2 and root 2 over 2, which means that the tangent of this is 1, because when you divide something by itself you get 1, and for these you end up just having the denominators cancel when you take tangent, which is quite nice. Although yeah, let me not mix it up too much. So sometimes, like if you say, okay, let's say we're trying to find the sine of 2/3 pi, or 2 pi over 3. I would be like, okay, let me convert this to degrees. For me, sometimes converting it to degrees is helpful. Okay, that's 120 degrees. So 120 degrees on my unit circle, it's only 30 away from 90. And actually you can see it up here quite nicely. So it's closer to the earth, so I know the horizontal displacement would be just a negative a half. But then this is the taller version, so that's √3/2. So now I have my cosine and sine right there. Well, let's say we're trying to get the tangent now. I got to do this y over the x. √3/2 divided by -1/2. Well, these 1/2 could cancel. It's just -√3 is the tangent of that 120 degrees, or 2 pi over 3 radians. So I know it's a little messy in my notation, but hopefully you're able to follow. It's just a way for me to figure out, without a calculator, all of these angles should be, and all of these trigonometric ratios should be ones that you can find in your head. And this is, then we get into these inverse tan functions. Sometimes you may see them written this way. And I believe that is equivalent to, you can see this here, right? That's equivalent to this little inverse sine, theta. So you'll see it written both ways sometimes. Oh, look, right here they have it, alternate notation. But all that's meaning is, let's say I have the arc sine of, let's say, 1/2. That's saying, well, sine of theta has to be 1/2. So what value of the angle gives you a sine of 1/2? Well, for me to think about this, so that's a y value of 1/2. So I believe it would be 30 degrees, because that's where it's more short than it is wide, right? It's wider than it is tall. So if you were to evaluate the arc sine of 1/2, if you were to do it in degrees, it would be 30. If you were to do it in radians, it would be pi over 6 radians. So the interesting thing here is, look at this. This is what I had to research the other day, that we have some assumptions. So for sine, we only consider from -pi/2 to pi/2 in that range, right? So what that means is that we our arc sine is always going to be an angle that falls in that range, or -90 degrees to +90 degrees. For cosine, because positive and negative are right to left, we consider from 0 to pi, or 0 to 180 degrees. But tan, it's the same domain considerations as sine. So hopefully this was helpful a bit. These laws haven't come up too much with what we've been doing lately, but those are included here. And shout out to Paul Dawkins, who wrote this back in '05, for giving us a nice guide. I'll post this PDF. Hopefully this video is at least a little bit helpful. And if you watch a double pace, it's only going to take you about 4 minutes to watch. Much love.